going to end. It won't happen for billions of years, but there is no way out. Figuring out how it will end is the challenge of astrophysicists around the world. They're pointing high-tech equipment out toward the heavens to unlock the secret of our fate. The possibilities are frightening. In one scenario, gravity pulls the universe back into itself, similar to air being let out of an inflated balloon. The universe goes back to its original size. This is the Big Crunch.
That'd be the end of the universe in a big fireball as all the matter collapses onto itself. That'd be pretty dramatic.
Then there's the Big Chill. The universe expands until the nuclear furnaces that power all the stars burn out. The universe grows cold and dies.
A second possibility is actually kind of sad. The universe will continue to expand forever, and it will just grow into an increasingly cold and lonely place as the expansion removes our nearest neighbors from us, and we just end up a single isolated community of stars and galaxies.
Then again, there could be a much more spectacular end in which everything is ripped to shreds, down to the last atom. Think of it like a balloon that is filled with too much air. It pops.
It's much more dramatic than the Big Chill, and just as fateful as the Big Crunch. The universe continues to expand, but at an ever-quickening pace. And in fact, the pace is so great that even the space-time fabric cannot hold the universe together.
However the end comes, it will be a dramatic conclusion. To understand how it all could end, scientists turn to how it began. The mystery starts to be solved here, at the Mount Wilson Observatory overlooking Pasadena, California. In 1929, while looking through what was then the world's largest telescope, Edwin Hubble makes a strange discovery. The universe is expanding.
Hubble's discovery led to a whole new picture of the universe, that it was a dynamic environment and that it evolved. It changed in time, and that's different from pictures that people had of cosmology previous to that.
Before Hubble, scientists said that the universe was static and unchanging. Hubble's discovery that the universe is expanding meant it had a starting point, a beginning.
That brought the idea forward that, hey, what if we ran the film backwards in time and found the point at which that began?
The Big Bang. That fraction of a second when the universe and everything in it exploded into existence from a point smaller than an atom.
One common misconception about the Big Bang is that we can identify a point in space where the Big Bang occurred. But in fact, it's more appropriate to think of the Big Bang as a simultaneous creation everywhere of space, which is then continuing to expand to the present day.
Scientists theorize that at the moment of the Big Bang, the first small particles of matter called quarks were produced. They collided to form the building blocks of the universe. These floated in a thick fog of hot plasma for about 400,000 years. Gravity, also created at the Big Bang, drew the particles together, eventually creating the first stars and lighting up the cosmos.
The theory of the Big Bang is a very solid theory. What happened at the moment of the Big Bang is still something we're working on. We don't really understand.
If the universe has been expanding since the Big Bang, scientists must consider that it will stop expanding at some point. The question is, how? The most obvious answer involves gravity. What goes up must come down. Stars and galaxies and everything else might reverse direction. The universe would collapse in what some scientists call a big crunch.
Take the top and then see the other handle and just jerk them apart.
A model rocket offers clues to how the big crunch would work. The rocket is like the universe expanding into space out of the Big Bang. An initial bang allows the rocket to overcome the pull of gravity.
5, 4, 3, 2, 1.
Eventually, when the fuel is exhausted, the rocket coasts a few feet higher, stops, and is pulled back to Earth. This is what would happen with a big crunch. The entire universe is essentially pulled back to its launch pad.
The universe itself has its own momentum, its own energy, it's moving outward, but eventually there's a point where possibly the universe will stop that moving outward, just like the rocket that we saw, and have to fall back in upon itself and collapse again under the force of its own gravity.
In this scenario, the universe could return to its original state just before the Big Bang, setting the stage for a perpetual seesaw of creation and destruction. The Big Crunch theory moved to a scientific back burner. Cosmologists figured out that there must be some form of energy that keeps the universe from collapsing. The existence of such a force leads to new theories about what the universe is made of and how it might end. And evidence about how this might play out is found in some of the most powerful and mysterious phenomena in the cosmos: black holes. Predicting how the universe will end involves some of the most advanced technology known to man. On a remote volcano on the island of Hawaii, astronomers are monitoring a battle in space that is shaping the fate of the universe. At an elevation of nearly 14,000 feet, the Keck telescopes bring astronomers from all over the world nearer to space for a clearer view of the cosmos. They come here because the telescopes work best far away from city lights and as high as possible above Earth's polluted air. Harsh conditions make it difficult to work here, but for scientists in pursuit of the great mysteries above, it's paradise.
So this is a remarkable location, but of course the air is very thin, it's extremely hard to work here, but these telescopes are amazingly powerful. But we're ambitious astronomers. We don't just stop looking at easy objects. We try hard to look at the very faintest objects so we can understand the extremities of the universe.
Here, astronomers like Richard Ellis are working on a problem that has been all-consuming for cosmologists since Edwin Hubble. They know the universe is expanding, but what they don't know is how fast. It will be difficult to predict exactly how the universe will end until they solve this mystery. The answers lie in the past.
Now what I did the focus on was a V equals 12.
There it is, yeah. Okay, that's the dry star.
Get a better focus now, that was worth doing.
An astronomer like myself uses a ground-based telescope as a time machine in times to study distant galaxies seen as they were a long, long time ago.
One of the distant galaxies that astronomers found revealed a powerful source of X-rays from something that they could not see. It was in the constellation Cygnus and emitted no light, but something was there. Whatever was emitting these X-rays had a mass about 7 times that of Earth's sun. There wasn't a name for it, so they called it a black hole. Black holes offer scientists an analogy to how the Big Crunch theory works. When certain stars run out of fuel, they collapse in on themselves into a smaller and far denser mass that attracts more and more matter, just like the Big Crunch. The gravitational pull is so powerful that anything that falls near a black hole will be forever trapped. Not even light can escape. It's a mind-boggling concept that something invisible is detectable and offers a view to our ultimate fate.
This black tarp represents space, and space is relatively flat. But when you put a massive object into space, it curves it. This is a penny, and notice how it comes into a really beautiful circular orbit. Basically, the black hole trapped it into an orbit around itself. And that orbit becomes very circular as it gets closer. And now the penny will eventually disappear, go inside the black hole.
Earth's sun warps space similarly to a black hole, only it's a cosmic wimp by comparison. The gravitational pull of our sun is much weaker. Earth and all its nearby planets are trapped by the sun's pull, but it's so mild that it just stays in orbit without being sucked into the sun. The mass of a black hole can be 1,000,000 times the mass of the sun, or more, causing a huge warp in the space around it that consumes everything that comes near.
That black hole wraps space around itself. And so if material falls near it, it falls inside and gets trapped forever.
Black holes exist in isolated areas throughout the cosmos. A black hole's gravitational pull is a scaled-down version of the force that could cause the universe to collapse. That force is dark matter, and dark matter is what scientists often call cosmic glue.
Hi, Matthew. So let's do some cosmology here. Dark matter attracts other objects via its gravitational attraction. It's a positive force.
There's another force that opposes gravity, and that is dark energy.
Dark energy, we don't really understand what it is, but it's a negative repulsing effect that pushes galaxies away from each other.
The whirlpool in Richard Ellis's demonstration represents the gravitational force of dark matter. The green dye coming out of the syringe shows how the stuff of the universe collapses under the force of dark matter.
The presence of dark matter acts as the focus for the gas in the universe, bringing structure together. This is how the Milky Way developed as the universe expanded. Little things merging into big things, the positive, constructive force of gravity. Now, if this was the only force in the universe would stop expanding at some point in the future, and eventually the universe would start collapsing. Gravity would eventually halt the expansion, bring it back together in a big crunch.
Yet the universe continues to expand and isn't showing any signs of collapsing. This suggests the opposing force of dark energy could be stronger than dark matter. But it will take scientific detective work to find out. They look to one of the most violent forces in the universe for clues.
We're studying exploding stars to try to understand if they can tell us the rate at which the universe is expanding.
These are explosions at the end of the lives of stars, not unlike our sun. The fuel that these stars have in their centers is spent. The star collapses, the outer part expands, and the star becomes something called a white dwarf.
White dwarf stars sometimes have other stars orbiting nearby, a companion star. A massive explosion could happen if the companion star's debris falls onto the white dwarf, causing a spectacular fireworks display in the cosmos. Scientists consider exploding stars, or supernovae, like in these images captured by the Hubble telescope, to be reliable telltales of how fast the universe expands. Their brief and bright explosions allow scientists to track the universe's expansion and give them a way to measure its speed.
Essentially, they are white dwarf stars that become nuclear bombs. They explode with a certain brightness and a certain length of time. It takes a certain amount of time for that brightness to dissipate. They are essentially standard candles. Any one of these will look the same no matter where it is in the universe.
Astronomers measure the distance and speed of these exploding stars by measuring the amount of red light they emit. The faster the star moves away from us, the redder its light appears. The expansion rate of galaxies containing stars like supernovae can then be used to interpret how the rest of the universe is moving outward.
We know this because we can compare the velocities of galaxies with their distances.
These are the clues that lead astronomers to answer just how soon the universe will reverse direction and come back together in a big crunch. Or, this information might lead to an entirely different conclusion. Dr. Ellis is looking at clues at the Keck Observatory in Hawaii. While the telescope is on the top of a huge volcano, he's in a viewing room on another part of the island.
Hey, emission lines, Johan.
Oh, you see it?
In the red side, I think.
At the same time, Johan Richard is at the California Institute of Technology in Pasadena, California, evaluating the light from a distant galaxy that the Keck telescope captured in Hawaii. He's looking to see if any of the known elements coming from the galaxy are in the red spectrum and moving farther away.
We can interpret that as a velocity, as how much the galaxy is moving away from us. We can really interpret how the entire universe is behaving, is expanding.
Interpreting redshift is the cornerstone of the quest to pin down the fate of the universe. Clearer pictures of the universe that have only been possible in recent years have led cosmologists to conclude that the redshift of distant galaxies is greater than predicted. This is startling. Not only is the universe expanding, it's speeding up. Nothing in the observable cosmos could account for an accelerating universe, and yet the data seem irrefutable. This has to mean that an invisible force is working against gravity. Cosmologists have come up with a name: dark energy.
So when the universe was young, gravity was the most dominant force. And so what we see here is galaxies as particles on the surface of the water are bound together by gravity. And at a point about 7 billion years ago, dark energy and gravity are pretty well in balance. But the universe continues to expand, the density goes down, and so dark energy starts to take over. And lo and behold, the universe starts to accelerate. So dark energy is now the dominant property of space.
So the universe started out with a certain amount of energy, and we know we're trying to understand how much energy there is, and we know the universe is expanding as it moves outward with time. We also know now that the universe's expansion is accelerating, and we don't know, is that acceleration going to slow down or not? We're still trying to understand that. So in understanding what's going to happen to the fate of the universe, we have to know how much energy is there, how much matter is there.
The history of the universe is really a battle between dark matter and dark energy. These two forces are in opposition, and so both the history of the universe and its ultimate fate is really the competition between these two forces.
The Big Crunch theory was a result of scientists interpreting that dark matter is the dominant force. But astronomers now suspect that dark energy might be much stronger. If so, the end could be dramatic and violent.
It pulls apart solar systems, it pulls apart stars, and eventually it grows so strong that it pulls apart matter itself, breaks bonds, pulls apart atoms, and reduces everything to fundamental particles, and that's the end of the universe.
The battle between dark matter, the force that holds the universe together, and dark energy, the force seeking to tear it apart, has set the universe on a path of destruction. If dark matter is the victor, the universe might collapse, If dark energy rules the cosmos, it could rip to shreds.
The expansion grows so strong that it tears up the entire universe.
It'll be a strange twist of fate. Dark energy, the force that propelled matter to form a magnificent universe, continues to push it outward and drives it to its demise. To find out if dark energy is in fact winning the battle, scientists will first need to know how fast the universe is actually expanding.
The most remarkable feature of the universe is that it's expanding. Every galaxy is moving away from every other galaxy. When you look out into the night sky, you see distant stars, galaxies, clusters of galaxies they observe with telescopes, and they're all moving away from us. We can illustrate that with this balloon. As we expand it, we see that every dot drawn on this black balloon, like the night sky, is moving away from every other dot. But there's something else that we know about the universe, something else that we know about the expansion. That is that the expansion is getting faster. The universe is accelerating. The size of the universe is getting bigger at a faster and faster rate. And we don't know exactly how fast it's accelerating, but if it's accelerating fast enough, then something really dramatic could happen. The universe could end up tearing itself apart in a big rip.
This is perfect. This is great that you rigged this up. So this is a giant version of the demo that I do in class.
Dr. Robert Caldwell attempts an earthbound experiment to show how dark energy affects the acceleration of the universe. He uses a paintball gun mounted on a truck.
Yeah, and basically, I mean, we could adjust the angle in any way that you want it. What do you think about this?
I think down at the ground,
a little bit more
is the best, so we can mark each time the gun fires. That'll be good.
Let's try that.
He sends the truck coasting down an incline. Earth's gravity pulls the vehicle downhill, which is similar to how dark energy propels the universe outward, causing it to expand. Gravity pulls the truck forward at an increasing speed. The gun fires paint at the ground at regular 1-second intervals. Caldwell measures the distance between the paint dots to calculate just how fast the truck was accelerating. He'll use the data from this experiment to see how gravity's force compares to dark energy's force in the cosmos.
We started thinking about the Big Rip when it was discovered that the expansion of the universe was accelerating. The degree of acceleration is not known, and it's the subject of a lot of effort by astronomers today to try and figure out exactly how fast the expansion is growing. What is the past evolution of the universe in detail, and if we can glean from that, what is the future evolution of the universe? It's not known exactly how fast it's accelerating. There's some evidence that the acceleration is beyond a certain threshold, and beyond that threshold, there's a runaway effect that could take place, and it would rip apart the universe.
Good luck.
Fantastic. I think we've got some good data.
Excellent. How do we measure this?
Great. Give you that end.
All right.
I'll take this.
5 feet 8.5 inches.
The point of the paintball experiment is to find parallels between the truck propelled by the invisible force of gravity and the accelerating universe.
I'm glad we got the long tape measured because it's really growing pretty fast, the interval.
Within a few measurements, the distance between the paint spots increases by nearly 7 times. If the truck were in space, at this rate, it would travel faster than 100 miles per hour within a minute, and over 1,000 miles per hour within 10 minutes.
They're getting big now.
Here we got 42.5 feet.
42, all right, 0.5.
The question for Robert Caldwell is whether the same kind of expansion and acceleration are happening on a cosmic scale.
What's the capsule made of? Is it plastic or some kind?
Gelatin.
Okay.
It's all biodegradable.
So
you could actually eat them if you wanted to.
This right here is the data that I took with Eric, the cumulative distance traveled by the car as a function of time.
You point the space telescope at a single region in space. And if you looked at this from a typical ground-based image before Hubble was launched, first of all, it's literally almost size of a postage stamp. And so suddenly, the first Hubble Deep Field that was ever taken had 4,000 galaxies that looked just like the galaxies here, that were never visible before from the ground. A tremendous power. Each of these smudges in their own right is another galaxy. Each one of these galaxies contains about 100 billion stars.
Hubble sees more than just stars and galaxies. It just might be onto one of the key ingredients of space, an invisible ingredient that could put the brakes on dark energy's effect and cause a big chill. That's dark matter. Scientists talk about dark matter as the substance that holds the universe together and could prevent a big rip. Evidence that dark matter exists is seen in some of Hubble's images of nearby galaxies. It sometimes appears as though other galaxies surround them. The other galaxies are not really there at all. Rather, they are reflections of more distant galaxies coming from behind. Astronomers suspect this optical illusion is dark matter causing a weird distortion of light called gravitational lensing. The light from the more distant galaxies is literally bent by the curvature of space caused by stars and dark matter in its path. The more dark matter there is between Earth and the distant galaxy, the more the light will be bent and the greater the force to cause a big chill.
The gravitational lensing is a tremendous tool for the astronomer because we can measure the distortion in background galaxies and use it to trace the distribution of dark matter on various scales. We're looking at a distribution of idealized galaxies here on the sky, and the light from these distant galaxies is passing through clumps of dark matter. What you look at is not really what's happening. It's a bit like wearing spectacles and not knowing that you're wearing them.
And if you can tell how much that bending is occurring, you can map the dark matter, and you can also see, well, if there's dark matter there, is the universe around that dark matter behaving the way it should given the gravity or not? If it's slightly gravitating less, then dark energy might be changing in those places.
Identifying which energy force dominates, dark matter or dark energy, will give scientists more confidence about whether a big chill or a big rip will be our fate. The best evidence shows dark energy as the driving force, but by how much? Solving this mystery depends on astronomers finding ways to measure how fast the universe is moving. On Earth, it's simple to determine how fast something moves. An airplane, for example, is relatively close. We can look at it and calculate its speed by estimating the distance it travels and timing how long it takes to get from one point to another. But a star's light can travel for millions or billions of years before it can be seen on Earth. By the time its light gets here, the star will be long gone, and it's too far away to gauge its speed or distance traveled with any certainty. The universe is expanding, only scientists cannot give precise answers about how fast. The mystery moves closer to being solved by imaging the cosmos with greater precision. Clearer images from space make it easier to estimate the rate of expansion.
If the universe continues to expand with time, then ultimately all of the energy sources, the nuclear furnaces and stars, would run out and die, and the universe would actually get very cold, and there'd be something called a big chill.
In the big chill scenario, Earth could become a lonely, cold planet as the universe expands. Distances between stars grow so vast that they nearly disappear from view. Over time, they burn out, and eventually the entire universe ends in a frozen state. This sphere demonstrates the principles behind a big chill. The marbles coming out of the sphere are like stars that were formed following the Big Bang. Dark energy propels the stars outward, dark matter slows them down. In a big chill, the expansion would continue, but the nuclear fuel that causes the stars to burn will eventually run out. From Earth's perspective, the first thing to go would be sunlight. The sun dims as it exhausts its last bits of nuclear fuel. Earth would freeze and become lifeless. And billions of years after humans are gone, the cosmos expands out of view. A few newer stars might remain, but most would have long moved away. The furnace powering the universe burns out. The darkened universe continues to expand, a frozen and lifeless remnant of its once vibrant existence.
Eventually, if this keeps going, if nothing changes in the composition of this energy density, the universe will continue to expand forever. It's going to get colder and colder, and eventually even our neighboring galaxies will be receding from us so fast that we won't be able to see them. So the universe is going to get cold and dark, and it will be a very lonely place.
Astronomers have much to learn about the influence of dark energy and dark matter, and much of the newest information is coming from this probe in deep space. It's sending back information that's helping scientists to interpret the history and the fate of the universe. The night sky, by all appearance, is a quiet and peaceful place, but in reality, there are forces that are driving it to an end. Big science moves astronomers closer to deciphering the universe's great mysteries, including its ultimate fate. The solution to the universe's riddle may well be hidden in this multicolored image. What's incredible is that it's a map of the early universe from the moment it was conceived. And even more fantastic, it reveals a great story that helps cosmologists predict how it will end. The machine that captured this is called WMAP, a NASA satellite that's working around the clock to chart the cosmos.
What we're looking at here is the edge of the visible universe. It's the light that WMAP measured, it's the remnant heat from the Big Bang, and this is literally the oldest light in the universe that we can see. This fossil relic from the early universe tells us a great deal about what the composition of matter was like, what the expansion rate was like, and really what the conditions were at the birth of our universe.
WMAP is one of the great astronomical breakthroughs of the 21st century. Nothing before could give us such a clear image of the energy left over from the Big Bang, energy that scientists call the cosmic microwave background. WMAP is measuring temperature differences in the cosmic microwave background, which may finally make it possible to predict which force will dominate the universe and how that force will bring the cosmos to its end.
The blue spots are regions in the microwave light that was produced by the Big Bang that are slightly colder than the average temperature, and the red spots are regions that are slightly hotter than the average.
Temperature differences revealed by WMAP tell scientists about the nature of the matter and energy that is contained within the universe. They're able to analyze the light patterns and find clues not only about the substance, but also the fate of the universe.
We only capture a tiny part of the electromagnetic spectrum with our eyes, and we have to go to much longer wavelengths. The same wavelengths that are used to heat water in a microwave oven are what we're measuring here with WMAP.
WMAP is so precise that it can detect differences in temperatures as small as 1/1000th of a degree. This sensitivity helps scientists to calculate the ratio of dark matter to dark energy, forces that will determine how the universe ends.
We assembled all those difference measurements and make a map of what the variations look like. And by turning up the contrast, we can basically subtract off this uniform glow from the Big Bang and look for variation.
It doesn't look like much until Gary Hinshaw adjusts the contrast. Then the WMAP image comes to life. Looking at WMAP imagery is in essence taking a journey back through space and time so that we might get some new ideas on the fate of the universe. Pulling away from the probe and following the path of the light it is collecting, we pass Mars, Jupiter, and Saturn, whose reflected light takes over an hour to reach Earth. Then, leaving the Milky Way, we pass Andromeda, the next nearest galaxy, whose light takes 2.3 million years to reach us, which means we have traveled 2.3 million years back in time. And finally, we arrive back 13 billion years ago, at the beginning of visible light. Before that, superheated hydrogen gas is everywhere. WMAP can see this far back in history. It's confirming important facts about the universe and what's driving it to its demise. The final act for the universe becomes more easily predicted thanks to WMAP. Its information, combined with the work of astronomers, has led to some astounding discoveries concerning a rapidly expanding universe. Rapid expansion supports the dark energy theory and the possibility of a big chill or big rip.
We now know from all the data we've had in the last 10 years that there's, by a factor of 2 to 1, more dark energy than dark matter. So dark energy is the dominant constituent of energy in the universe.
The evidence seems clear. Dark energy is taking over and is leading astronomers into new thoughts about the beginning and the end of the universe.
Before the discovery of dark energy, things were a lot simpler. If we could determine the amount of matter in the universe, then we could say something about its ultimate destiny.
Those simple days are gone, but the proof is adding up and supports the idea that the universe will continue to expand. But will it do so to oblivion?
We've made huge strides over the last century in learning something about the evolution of the universe and its expansion. But we've now raised more questions in some sense than we've been able to answer. And so I think the next decade is going to be even more exciting.
Astronomers have tons and tons of challenges that have been thrown our way by theorists, and we are rapidly trying to figure out how to answer all of these questions. And I think that's the exciting future, because if you can go out and really observe something, you're testing it. And that's what science is all about.
The battle between dark matter and dark energy is expected to go on for billions of years, and humans will be long gone from Earth when the final outcome occurs. But no pursuit has been more significant to science than understanding how the universe arrived, how it works, and how it will end.
It's a never-ending quest. It's driving astronomy. What are the answers to these profound questions? The constituents of the universe, the nature of dark matter, and perhaps the biggest mystery of all, what is the ultimate fate of the universe?
Our nearest star. In the fall of 2003, it unleashed an eruption of energy equal to 200 billion hydrogen bombs, blasting a tidal wave of superheated charged particles at speeds of up to 6 million miles an hour. It was one of the largest solar storms ever recorded. and it was aimed at Earth.
They were some of the fastest, hottest, and strongest storms ever measured.
Assaulting the Earth, the sun's energy forced space station astronauts to take cover in their most sheltered compartments. Lights went out. Communication streams were cut. Airliners scrambled for safety.
This really was a hurricane of space storms.
Though no major damage was done, these storms were a stark reminder that we live at the constant mercy of the sun. It controls all aspects of our lives, our climate, our food, our bodies.
We actually live inside the sun's atmosphere. We, along with all the other planets, are greatly influenced.
But is its influence changing?
It's actually growing more powerful.
Might we lose its protection from deadly cosmic rays?
At its boundary, where it's protecting us from the intergalactic winds, that boundary is actually shrinking a bit.
Will our technology-dependent society be able to handle another solar superstorm?
Sometimes these effects can be so severe that they're catastrophic.
And when will the next superstorm strike?
One, go for drop.
Pegasus is away on the IBEX mission. All Pegasus.
Fall 2008.
Stage 1 ignition.
NASA launches IBEX, the Interstellar Boundary Explorer. Part of its mission is to study the effects the sun has on the furthest reaches of our solar system. IBEX joins the long list of human attempts to explain our star's impact on our solar system, our planet, and our lives.
The sun. The sun provides all of our light and heat. If it weren't for the sun, we wouldn't be alive.
We people are very interested in what goes around us. We like to understand our neighborhood. The sun in the universe is our street, our neighborhood.
The sun. We are actually affected by its moods. In fact, it's like the parent, and all the planets are the children that are affected by its moods.
We need to know how it's going to evolve and how the changes that are always happening in the sun affect us here on Earth.
The sun. If we want to understand the universe and the stars that make up the universe, then it's important to study the one that's closest to us.
We've learned more about the sun in the past 40 or 50 years than in all of recorded history.
This golden age of exploration was kicked off by a unique mission that gave us close-up images of our sun from above our atmosphere.
Skylab, we're reading you loud and clear over the Vanguard for 8 minutes.
In 1973, Skylab became the first manned space station. It sent back images of the sun, clearer than anything taken from Earth.
The Skylab mission was one of the very first laboratories that was dedicated just for the research and study of the sun. In some ways, it's kind of the grandfather of the current missions today.
Right now, a fleet of about 20 space probes scan and study the sun in ways we never imagined, even 30 years ago. By studying the sun from the vantage of space, we can see it in a whole new light, using different light wavelengths, including X-ray and extreme ultraviolet. We can peel back its layers and begin to understand how and why the sun acts the way it does.
The different wavelengths mean different temperatures, and different structures are more visible in different wavelengths than in others.
Our robotic space probes never stop watching the sun. With their help, scientists are working out the big questions about our star, and we already know a lot. The sun is one of over 200 billion stars in our Milky Way galaxy, but it is our closest at 93 million miles away from Earth, almost the same distance as 4,000 trips around the globe. And despite that distance, its light only takes 8 minutes to reach Earth. It is only 4.5 billion years into its nearly 10 to 11 billion year lifespan. And though technically a medium-sized star called a dwarf, it is enormous, 900,000 miles across, and if hollowed out, 1.3 million Earth-sized planets could fit inside. The sun accounts for 99.8% of the mass in the solar system, and it weighs 300,000 times more than the Earth. It is made up almost entirely of a superheated form of electrified and magnetized gas called plasma. The sun packs enough gravitational pull to keep the planets from spinning off into space. And as Copernicus first suggested, it rules the center of our solar system with a gravitational iron fist.
Copernicus's model, in which he placed the sun in the middle of the solar system with all the planets going around it, instead of everything going around the Earth, was a giant paradigm shift. It meant that the sun is the most important thing in the solar system. It meant that we really should understand the sun.
Our sun, like all other stars in the universe, is made from the dust of stars that lived and died over billions of years, going all the way back to the Big Bang.
So our sun and our solar system is really the debris from many generations of stars.
The sun we see every day is the solar system's source of power. Deep in the center of our star, its core is superheated to 27 million degrees Fahrenheit and is the engine that drives it all.
Inside the sun's core, the process of fusion is occurring, and that fusion process is giving off light and particles.
Every second the sun shines, it releases the same amount of energy as 1 million H-bombs. The sun's light is made of particles called photons, born in the core, then propelled by convection currents through the radiative and convective zones of the sun. Eventually, they reach the volatile outer layers of our nearest star.
The sun's outer parts consist of 3 regions. There's the photosphere, or surface of the sun, and it's not really a hard surface like that of the Earth. The sun is gaseous throughout, and the temperature of the photosphere is around 10,000 degrees Fahrenheit.
Above the thin layer of the photosphere is another thin layer called the chromosphere. And the chromosphere is slightly hotter than the photosphere, which is counterintuitive because you would think that as you go away from the source of all the energy and heat, the core, that temperature would drop. But in fact, the temperature rises from the photosphere to the chromosphere, and it gets even hotter as you rise to the third layer of the atmosphere called the corona.
And then beyond the chromosphere is a large, tenuous, extended region, the corona, which is millions of degrees.
The sun produces a continuous outward flow of energy called the solar wind. Constantly blowing, it carries energy out into the solar system, extending our sun's reach 9.3 trillion miles, well beyond Pluto.
The space in between the planets and the space in the entire solar system is not an empty void, but it's full of these particles and it's full of these rays of light.
While the solar wind blows away from the sun, its gravity holds and pulls everything in. Take comets. All comets orbit the sun and can get pulled directly into the line of fire. Recently, scientists witnessed one of the sun's most dramatic outbursts, a coronal mass ejection, ripping the tail off a comet.
When it hit the comet, the tail was cut off like you took a knife, and the tail drifted away, and then it took a little more time for the comet to generate more gas and plasma and dust and create a tail. It tells us about how the solar wind moves in the solar system and how it can affect things.
The sun affects everything it touches, even us. To learn just how much, scientists sometimes rely on a remarkable cosmic coincidence. The lethal output of the sun has made studying it almost as difficult as understanding it. But scientists can get a good look at our nearest star thanks to a cosmic coincidence. A total eclipse of the sun.
A total solar eclipse occurs when, from our perspective, the moon is exactly aligned with the sun and blocks its photosphere. It's a glorious sight.
The solar eclipse is the most wonderful thing to see. It grows really dark by factors of thousands within seconds. And as it does become so dark, you can look up in the sky, you see the dark shadow coming from one direction, sweeping at you. It's really coming at thousands of miles an hour. So it's very impressive to see.
Humankind has marveled at the mysteries of the eclipse for millennia. Scientists have used it as an opportunity to see the sun's outer atmosphere, the enigmatic corona. One of the hottest regions of the sun, energy from the corona radiates out to the edge of the solar system.
The entire solar system actually sits in this outer corona of the sun. So this atmosphere of the sun is bathing all the planets.
The engineers who built the Solar and Heliospheric Observatory, or SOHO, installed an artificial eclipse into the space probe. Called a coronagraph, it does the same thing as a natural eclipse, blocking out the blinding rays of the sun, so scientists can try and answer an old question.
How does the solar corona get so hot? After all, the everyday surface of the sun, the photosphere, is only around 10,000 or a little more Fahrenheit. And the corona, on the other hand, is millions of degrees hot. If you go away from a stove, you know it gets cooler, but if you go away from the everyday surface of the sun, it gets hotter. And how is that?
It all starts at the sun's core, where every second, nearly 700 million tons of the universe's most common element, hydrogen, are converted into helium through nuclear fusion, giving off the energy that becomes photons, otherwise known as light.
The sun's core is really hot, several tens of millions of degrees. And there, the temperatures are so high that protons, hydrogen nuclei, can come together, grab each other, fuse, eventually into helium, and in this way, release energy.
What happens with these photons, they go through this process, what we call a random walk, where they have to go through the layer of the sun, they get absorbed and then reabsorbed into lots of different photons at lower energy level. So this process of being absorbed and reabsorbed millions of times can take 150,000 years.
Once out of the sun's interior, photons are only 8 minutes away from Earth, but they're leaving behind a world in constant motion. The solar surface boils. Energy rises constantly from below. Coils of plasma and energy, called coronal loops, spring across the sun. While dark regions known as sunspots stretch thousands of miles, and at only 7,000 degrees Fahrenheit, these sunspots are the coolest part of the sun, emitting less light than the surrounding area.
If you were to pluck a sunspot away from the sun and place it in the sky, it would actually be as bright as the full moon.
Sunspots appear on the surface and are easy to see. Their genesis, however, is tied to the sun's deep interior and complex rotation.
The sun doesn't rotate like a solid body. Instead, it rotates more quickly near the equator than near the poles, which leads to sunspots. The equator completes one rotation in 25 days. Mid-latitudes complete one rotation in about 30 days, and near the poles, one rotation is completed in about 35 days.
Called differential rotation, this process makes the sun's interior churn at different speeds, creating intense magnetism in the form of millions of magnetic field lines, which get mixed up as the sun's interior twists up like a rubber band.
This builds up pressure, which makes them buoyant. So they float to the surface, and where they pop through the surface, they create sunspots.
Once on the surface, the now twisted and balled up magnetic field lines block the convection of superhot plasma from rising, making sunspots appear dark.
And when those sunspots start to twist around, you can imagine that you have one sunspot here and one sunspot here, and there's a magnetic field that connects the two. And that magnetic field gets twisted, and eventually the same sort of thing that happens with a rubber band, it pops. And when the magnetic field pops, it releases energy. And in the case of the sun and solar flares, it releases huge, huge amounts of energy.
The magnetic field lines created by the twisting and churning of sunspots, though invisible, can be seen in the dramatic formations on the surface of the sun, in the form of flares and prominences. It is here that the sun's influence starts, as the breaking of these magnetic field lines drives massive amounts of energy from our nearest star out into the solar system. And it is these magnetic field lines that are behind most theories on why the corona is so much hotter than the surface.
It's pretty clear that it has something to do with the magnetic field that heats the corona. But presumably there are waves along the magnetic field that bring energy from underneath the surface of the sun into the corona.
The solar probe Hinode, which means sunrise in Japanese, was launched in 2006. Its mission to study the interaction between magnetic field lines and the corona. Recently, it captured images of one of the waves thought responsible for heating this enigmatic region, Alfvén waves.
Alfvén waves are waves that occur in a plasma, in a bunch of ionized gas, threaded by a magnetic field. And indeed, it's thought that these Alfvén waves might be bringing turbulent energy from inside the sun out to the corona, where that energy heats the corona.
Energetic Alfvén waves form inside the sun and travel up through the surface, making the looping magnetic field lines sway and vibrate.
And so through this vibration or this oscillation, they're having friction with the magnetized plasma surrounding it in the corona. And through this friction, heating occurs.
It's this heat, delivered to the corona, that radiates out into space, filling our solar system with the sun's energy. But this energy is not constant. Our sun is an ephemeral body, never the same from one day or 1 year to the next. Like Earth changes with seasons, so does the sun. And when the solar seasons change, anything can happen. Day in and day out, the sun we see appears the same. But like Earth, the sun has seasons, solar minimum and solar maximum. Two distinct personalities that can affect our technology and possibly even our weather. The transition between solar minimums is called the solar cycle, an average 11-year period in which the sun's activity maxes out, then ebbs again.
The primary measure of the solar activity cycle is the number of sunspots visible in the sun.
During solar minimum, the period with the fewest sunspots, solar activity is limited. When sunspots break through the surface during solar max, the sun's power reaches out.
When there are lots of sunspots, there are lots of flares and coronal mass ejections.
Increases in solar activity enhance the connection between sun and Earth. Energy expelled from the sun can create disturbances in the near-Earth environment.
The Earth is embedded in the solar atmosphere, and so what happens on the sun affects the Earth, and that's what we call space weather.
Accurate space weather forecasting is the ultimate goal, but this can be hard. The sun is turbulent, especially during solar maximum, the peak of solar storm activity.
During solar maximum, the magnetic field of the corona becomes very complicated, and you have magnetic field everywhere, all around, even near the poles. You can have coronal mass ejections and flares and solar storms occurring sometimes several times a day.
Solar flares, violent eruptions of energy, usually near sunspots, burst into space. Like a bolt of lightning, quick and powerful, they can happen over a matter of minutes and can give off the same amount of energy as 1 billion megatons of dynamite.
Solar flares are gigantic outbursts of energy from the sun, coming from a very small localized region of the sun's surface. So they're very concentrated ejections of energy that heat the surrounding gas to 10 million degrees.
Solar flare is sort of like a snapping of the whip. It really releases a lot of energy very quickly, accelerating particles almost up to the speed of light.
The particles from the very most energetic solar flares can reach us in something like 15 minutes.
But the solar hurricane of space weather comes from coronal mass ejections. These massive blasts carry billions of tons of superheated gas and plasma into interstellar space.
So coronal mass ejection is where a huge amount of mass and energy is expelled away from the solar surface. So if you can imagine this huge amount of mass and energy traveling away from the sun at these large speeds, sometimes at over 1 million miles an hour.
They throw these like big bubbles of hot gas and magnetic field. It can move off the sun so quickly that it actually creates a shock wave. They're the biggest storms, and they're the important ones for understanding space weather.
Solar probes, like SOHO, have captured the sun expelling massive amounts of energy into space. But scientists are most concerned when they see something called the halo effect, when the cloud of energy appears to surround the coronagraph. That means the sun has aimed its latest blast at us, like in the massive solar storms of 2003.
The fastest coronal mass ejection ever studied in modern times came from these storms.
Shortly after the initial blast from the sun, SOHO was bombarded by charged solar particles, protons and electrons, overwhelming the camera and causing the image to drop out.
What happens is you see a sort of snow on the camera, all sorts of sparkles going by, and that's the particles accelerated by the coronal mass ejection hitting the actual camera on Soho.
If caught off guard, solar storms can harm astronauts, exposing them to the same amount of radiation in seconds that we receive on Earth in a year.
So if we're going to send astronauts back to the moon and to Mars, it becomes very important to be able to determine when these coronal mass ejections and storms are going to occur. The charged particles embedded in these coronal mass ejections are dangerous. It's a lot of radiation that would hit an astronaut.
Astronauts and satellites aren't the only potential victims of solar storms. The particles blasted towards Earth can interact with our magnetic field, occasionally wreaking havoc.
When this material comes smashing into the Earth's magnetic field, it causes it to ring almost like a bell. And when you have a magnetic field, and when that magnetic field moves, physics tells us it's going to create currents. And so electrical currents will be created in the outer atmosphere of the Earth. And these electrical currents can cause all sorts of disturbances.
The currents create problems for satellites orbiting the Earth. They disrupt global positioning systems. They can interfere with communications equipment, causing radio blackouts and knocking out mobile phone systems.
These mass ejections can send so many charged particles toward the Earth that some of them make it through the Earth's magnetic field and even reach power stations here on Earth, causing surges of electrons and power outages and short circuits and things like that.
In extreme situations, solar storms cause excessive radio interference and increased levels of radiation, requiring planes flying near the poles to be rerouted. But as powerful as the storms were in 2003, they're no match for what astronomer Richard Carrington saw in 1859, a super flare.
The super flare of 1859 was incredible because prior to this event, we didn't even know that flares existed. Carrington saw this huge bright flash on the sun with the unaided eye. And in order for him to see that, it had to have been a super huge flare.
There were reports of telegraph lines running without being powered.
We probably won't see another one that intense in our lifetime, although it's hard to say for sure. The sun has thrown us some surprises.
If a similar storm were to strike today, one recent estimate projects 130 million people would lose power, possibly for months.
Most of the electrical infrastructure, the power grids around the world would be knocked out. A lot of the transformers would be overloaded. Having a large portion of the population with no power for many months could cost huge amounts of money. People have estimated that it would be upwards of $2 trillion.
We won't know unless it actually happens, and the more warning we get, the more we can do to reduce the economic impact, which is one of the reasons why we're studying the sun.
Scientists are a step closer to being able to predict these storms since the launch of the Solar Terrestrial Relations Observatory, also known as STEREO. This pair of probes now gives scientists the ability to see the sun in 3D.
So now, when one of these coronal mass ejections travels towards us, we're actually looking at the side view. And so we can see how fast they're traveling, we can see how they're evolving, the structure.
In 2011, the STEREO probes will reach their ideal vantage point, opposite sides of the sun, giving NASA a 360-degree view, allowing them to see what is coming from the far side of the sun before it impacts Earth.
And so for the first time, we're going to have a complete view of the sun all the way around. So this is going to allow us to see everything that's happening on the sun at the same time, and this will lead us again into a better ability to predict these types of storms.
But as dangerous as solar maximum can be for its increase in space weather, the sun's solar cycle counterpart and calmer period, solar minimum, may come with its own dangers.
When there are a low number of sunspots on the sun, the climate here on Earth can actually cool a little bit.
2008 saw the fewest number of sunspots in nearly a century, with a total of 266 sunspot-free days.
In 2008, we were at sunspot minimum, but by now we expected to be climbing out of that sunspot minimum, and we're not. So this could mean that this particular sunspot minimum is more protracted.
Scientists believe that past protracted minimums have had a chilling impact here on Earth.
Now, every once in a while, the sunspot activity cycle seems to just go away or become much diminished. There was such a period around 1650 to the early 1700s.
There were only about 50 sunspots recorded, when normally in the same time frame there are tens of thousands. So it was a really low period of sunspots.
It was called the Maunder minimum. The sun was in a quiet state. And that was associated with lower than normal temperatures here on Earth. Europe experienced sort of a mini ice age during those few decades.
Whether or not this current minimum will be protracted enough to have such a large impact on Earth won't be known for years. But another measure of solar activity, the solar wind, appears to be waning. And that could impact Earth tomorrow. Bathed in the sun's atmosphere, Earth is shielded from deadly cosmic rays. And while the sun's power protects us, it can also harm us. Life on Earth survives this close to its star, thanks in part to its ozone layer. But what would happen if the ozone layer were gone?
If Earth lost much of its ozone layer, ultraviolet radiation from the sun would penetrate through the atmosphere and reach the Earth's surface.
The sun's massive amounts of ultraviolet rays would quickly eliminate most basic elements of the food chain, wiping out plants and then animals.
If we are bathed in huge amounts of ultraviolet light, eventually the life on the Earth would die.
But what could cause such a catastrophic collapse of the ozone layer? Something the sun is supposed to protect us from: a gamma ray burst.
Gamma ray bursts are intense, brief flashes of the most energetic kind of radiation known, gamma rays.
The most powerful events in the universe. In seconds, they give off the same amount of energy that the sun will emit in its entire life. They occur when certain large mass stars die or even collide.
They can be generated from very extreme processes, such as large mass stars collapsing into black holes.
They occur somewhere in the sky roughly once per day, and they come from very, very far away. Most of them are billions of light years away.
But just 8,000 light years away, deep within the Sagittarius constellation, buried in a pinwheel-like formation, looms a potentially ticking time bomb. WR-104. Two stars locked in a cosmic dance, spinning a full rotation once every 8 months. But one of these stars is on the verge of going supernova and emitting a gamma ray burst.
Now, one of these two stars is a very massive star that might someday form a gamma ray burst, and its beam might hit the Earth. If the high-energy beam from a gamma ray burst were pointing directly at the Earth, it could spell real danger.
The radiation from the gamma ray burst would be so intense, very short, on the order of 10, 20 seconds, but this would set up a chain of events which eventually would deplete the Earth of maybe 50 or more % of the ozone layer.
Scientists have speculated that a nearby gamma ray burst caused an ancient extinction on Earth millions of years ago.
At the time, there was only sea life that existed, and even though the sea life deep beneath the sea wouldn't be directly affected by the UV radiation, the plankton and the life on near the surface would die off, and therefore the food chain would be affected.
The threat is heightened even further by something scientists have witnessed over the past few decades: a 20% decrease in the power of the sun's solar winds.
The solar wind is the steady emission of particles from the sun.
They carry the magnetic field that is in the solar corona out into space.
It exists even when there are no coronal mass ejections or solar flares.
The solar wind continues way out beyond the orbit of Pluto and has actually blown a bubble in interstellar space.
Now that's a bit of a protective bubble because the magnetic fields protect us from charged particles coming from outside.
Normally, solar winds stream off the sun in all directions at speeds of 1 million miles per hour. Pulling the sun's invisible magnetic field along with it, they form the solar system's defense against intergalactic intrusion, the heliosphere.
The heliosphere is the very boundary where the solar wind hits intergalactic space. So it's this shell that's surrounding the sun and the solar system where it protects us from intergalactic winds here on Earth.
Recently, scientists have learned that the heliosphere is shrinking and getting weaker.
The solar wind pressure has been measured to be decreasing over the last 25 years. In fact, the heliosphere, where the solar wind pressure is extending out to, has actually shrunk a bit.
A weaker heliosphere increases the possibility that Earth will be exposed to harm from intergalactic cosmic materials.
So if there's less solar wind, then the heliosphere itself is going to shrink. That makes it easier for more cosmic rays to enter into the solar system.
Already, the amount of high-energy electrons, a small but telling aspect of cosmic rays around Earth, has jumped in number by 20%.
Looks like the cosmic ray electrons have increased, and you would expect that. If the solar wind has decreased by 20–30% over the last 15 years, the bubble will have gotten smaller, and you expect an increase in galactic cosmic rays.
The good thing for us is that we live on a planet with a thick atmosphere and a magnetic field. So we have two types of shields that protect us.
But that could change when WR104 emits its gamma-ray burst, possibly upsetting the balance of Sun and Earth, a balance that may already be in jeopardy because of something the Sun did billions of years ago. Over billions of years, the Sun and the Earth have developed the perfect balance for life to thrive. Sitting in the Goldilocks position of the solar system, not too hot and not too cold, the Sun gives us just enough light, just enough heat, and just enough energy to fuel our planet and our lives.
The Sun drives everything on the Earth. The Sun is the energy source of the Earth. So all of the energy that's given off by the Sun heats up the Earth. This drives weather. On a larger time scale, this drives climate. So basically the Sun is the energy source. It's the battery that drives the whole Earth environment.
Plants harness the Sun's energy through photosynthesis, creating carbohydrates. People and animals consume these carbohydrates, converting them into energy we can use. Even the fossil fuels that power our lives were created by the Sun. But our increased use of fossil fuels seems to be upsetting the balance between the Sun and the Earth.
Since all living material gets its energy initially from the Sun is the source of the fossil fuels, whether it's trees, whether it's other things that have been trapped in the rock layer and then squeezed and slowly over millions of years made into the hydrocarbons that we know them as. And we then harvest and use those from underground.
The fossil fuels that we burn today unleash the Sun's energy from millions of years ago, overwhelming the balance struck between our planet and its nearest star.
If we burn all this, we will change the atmosphere unrecognizably long before we get to a point when we're actually running out of the resource itself.
Already, we have seen the effects of too much solar energy in the rise of global temperatures. The release of millions of tons of ancient solar energy stored in fossil fuels has amplified the necessary and natural process called the greenhouse effect.
Many people think that the greenhouse effect is a bad thing. Well, in fact, it's not. It keeps the Earth warm. Without the greenhouse effect, Earth's oceans would be frozen solid. What is bad is too much of a greenhouse effect. If there's too much carbon dioxide and water vapor and methane in the Earth's atmosphere, then those gases trap too much of the Sun's radiation, elevating Earth's average temperature, leading to global warming. Now that can cause a melting of the polar caps and a rise in the ocean levels, leading to just a calamity on Earth if it happens too quickly.
Not only will our atmosphere continue to trap more heat, it could start to decay. Continued use of fossilized solar energy will allow in undesirable amounts of radiation from our Sun. Right now, our ozone layer prevents the majority of the Sun's ultraviolet radiation from reaching Earth, while allowing just enough sunlight to give us what we need to survive.
Sunlight interacting with our skin produces vitamin D, which is a very useful vitamin.
Vitamin D can protect us from a number of diseases, including the bone disorder osteoporosis and heart disease. But here, too, a balance has been struck. Too much sun can alter our DNA, causing skin cancer. Maintaining the equilibrium between Sun and Earth that allows life to thrive will require using less of the Sun's ancient energy and more of the energy it delivers on a daily basis. After all, the Sun's energy output is estimated to be 386 billion megawatts. Meaning in 15 minutes, our star radiates as much energy as all life on Earth consumes in 1 year. Tapping this power source has been the goal of scientists for decades.
For sheer size, a solar satellite would be unprecedented. A structure 35 to 40 square miles covered with solar cells, able to capture the sun's energy 24 hours a day and beam it to Earth.
NASA has yet to achieve a goal on that scale, but their work with solar technologies in space has advanced technology here on Earth.
History of solar cells is essentially a technology that came back down to Earth from space. When we first started to work on the Apollo and Mercury and Gemini programs, we needed power plants in space. Solar cells were a natural way to do that.
Currently, we have two ways of directly harnessing the sun's energy. Solar thermal, which converts the sun's energy into heat by concentrating it enough to drive turbines, and solar panels, which use silicon-based technology to directly convert the energy from above into electricity. We can indirectly tap into the sun's power through wind turbines, capturing the energy produced by the weather the sun helps create. These technologies are constantly being improved. But some of the most interesting new science is coming from a very old process, photosynthesis.
There's some really exciting opportunities as we move from the world of semiconductor solar cells to organic ones.
Attempting to mimic Mother Nature, scientists have been able to create electricity from something found at the farmer's market, spinach.
There's organic molecules in spinach, in all green plants, but spinach happens to have a very convenient one, where you can harvest that peptide, that molecule.
Researchers were then able to put that peptide into a kind of solar sandwich, placing it between two electrically conductive materials.
And when it's exposed to sunlight, it will circulate electrons, which is current, which is electricity. So these organic molecules can actually become little solar cells.
In order to maintain the balance between Earth and our nearest star, it's become clear we must focus on finding ways to fuel our lives with the energy the sun supplies today. After all, the promise of solar energy is that for as long as the sun shines, its power can be ours. But what will happen when its power becomes too plentiful? The elements that make up the sun, the earth, and even humankind all come from one place: stardust, the remains of stars that lived billions of years ago. And just as those stars died, so too will our sun.
In about 5 billion years, the sun will pretty rapidly become much more powerful, much brighter, and much bigger.
The sun will reach a stage where it has burned through all of its hydrogen. And once that happens, it will start to burn through all of its helium.
The sun will start to expand as it reaches a stage called a red giant. As it expands, it will start to expand into much larger size and fill the inner solar system.
The orbits of the planets themselves will actually expand outward as well, because it's not as massive.
During that stage, some instabilities, which I call cosmic burps, will cause the sun's outer atmosphere to be gently ejected.
The outer layers of the red giant will just keep drifting off at some slow rate.
The hot inner layers of the sun will ionize that cloud of gas surrounding it and cause it to glow. So our sun will be surrounded by these glowing clouds of gas.
They will form what's called a planetary nebulae. They're beautiful shapes. Some are just purely round, but some have been distorted into other shapes. They've come off non-symmetrically from the star underneath.
What'll remain is the contracting core of our sun. And it won't produce any new energy through nuclear reactions, because all the nuclear reactions will have stopped. So it'll continue contracting and slowly fading with time.
It's very similar to the process that creates, say, supernova, but our sun is not big enough, doesn't have enough stuff to actually create a supernova. So its final stage will be this object we call a white dwarf star.
What remains is this little, relatively small white dwarf star. And it is a very quiet, what we call happily retired star.
It'll be about the size of the Earth, it won't get any smaller, and it'll sit around as this very highly compressed rock forever. It'll just liberate its energy, growing ever colder and dimmer with time, until finally it just fades from view.
The death of the sun will have catastrophic effects on the solar system. If the massive expansion doesn't swallow the nearby planets, it will likely change their orbits and superheat them, including Earth.
Earth's surface will be fried to a crisp.
The Earth is probably going to get baked one way or the other.
I mean, imagine the sun being 100 or 200 times brighter than it is right now. Imagine how much the Earth would be heated. It would not be a pleasant place to be.
It actually may get baked before the sun completely dies, because the sun will get hotter even before it becomes a red giant and gets as large as the orbit of the Earth. It'll get warmer, and at some point the Earth will get hot enough so that water will boil.
So the oceans will evaporate away, and all of life as we know it will cease to exist.
If there's anything left of the Earth, the sun will shrink down to a white dwarf, and the Earth will, instead of heating, freeze.
This will not be a pleasant place to live.
But that's billions and billions of years from now. We've only had rockets in space, satellites, for 50 years or so. Now we're talking billions. So clearly we'll be able to travel around the solar system at the very least, to go to places that will be at the temperature that the Earth is now, and we'll be able by that time to go to more distant solar systems. So I don't spend a lot of time worrying about what's going to happen to the sun in 5 billion years.
The sun gave us our life, and it will eventually take it away. And though the Earth will die, it and everything on it will in some part live on. The stardust that gave Earth and all of its inhabitants life will one day become the stardust that gives rise